All right. Just a few administrative things. You know, last class we had to kind of end quick because of the fire drill, and so I didn't really get to wrap up what we did that day. Um, that's okay. I'm sure you all remember. You all went back and watched the video before you came to class today just to get freshened up on things. Um, we were doing line integrals, right? And line integrals, we said, were better suited if they were called curve integrals, because we're taking a curve, mapping that curve up into a surface, and finding the area of that curtain. That's what we were doing, right? So we're going to continue that today, but I want to talk a little bit about, first of all, the mini exam number 6 that you turned in last week. Was it last week that you turned in? Yeah. And I have not graded. I've been waiting on a few things, but I will grade those. Should have them back to you on Wednesday. And then on Wednesday, your mini exam 7 is due, which I sent out via email. Now, I know Canvas has been acting kind of screwy. Does everybody know how to get into their Canvas? You log in like you're going to go into ACES, and they have a link now in the middle of the screen. It's in red. Go there, and it'll take you to Canvas. So if you're having trouble getting there, let me know. Well, how many questions is on that mini exam 7? 4? 4? Okay. It's definitely not as tedious as mini exam 6 was, as far as like all the computations. So I'm hoping that it'll be okay for you. It really is making sure you understand the difference between cylindrical, spherical coordinates, and you know, if you have questions, come ask me. One thing I will point out after talking to a couple of students, one thing that I want to talk about is if you're doing a triple integral, the first type that we looked at, we said that in a triple integral we had as region E. It was three-dimensional, right? Because our function is in the fourth dimension. That region, the first one we looked at was like a box, okay? And then we said, okay, the shadow of that on the ground, right? If this is the XY plane down here, the shadow of that on the ground is a rectangle, right? And so we said, oh, but a rectangle, the shadow being a rectangle, we know how to integrate over rectangles. That's a double integral, right? And that's what we did. Then we said, okay, the shadow could be a type 1 shadow. And then we said, oh, it could be a type 2 where it's sideways, like that, right? So we had type 1, type 2. Or we said the shadow could be what? The shadow itself could be a polar region. So we convert it to polar. In all of those cases, we looked at the shadow of the solid, didn't we? Spherical is the only set of coordinates where we don't look at the shadow projected onto the XY plane. Spherical is different, right? So if you have a solid and you cast its shadow down, it's a rectangle, a type 1, or a type 2. You just have a triple integral in Cartesian coordinates. If you cast a shadow down and it's polar, you now are in what's called cylindrical coordinates. If you don't look at the shadow and all your solid is actually created by just varying. Remember how I was trying to get to the projector that one day? I said, you know, how can you get to the projector? You walk out a certain distance, you turn, you have this phi, right? This angle. Spherical, in order to create the three-dimensional region, there is no shadow that you look at. That's what I'm trying to get at here. So on problem number, I don't know, what is it, 2 or 3? 3, I say do the triple integral in spherical coordinates. And most students that have been coming to me have been trying to find the intersection of the two surfaces and then cast the shadow down. If you do that, you're in cylindrical coordinates. Spherical is different. So just pay attention to that, because I don't want you to go and do the whole problem and do it cylindrical thinking you're doing spherical. Understand? Okay. Now, getting back to what we did last time, bring up my notes here. Oh, I also sent out a bonus. That bonus question is due Wednesday. Now, I will say this on the bonus. Be very careful that you explain what you're doing, because there's more than one way to approach the problem. If you just go and Google the volume of the intersection of two cylinders and come up with 16 thirds, that's not the answer. But if you come up with 16/3 and you just do what someone else did, I'll probably be able to notice it. And you won't get any credit at all. I want you to logically go through it. I already had one student talk to me about it. You know, you have a cylinder, you have another cylinder. Why don't you find the volume of both the cylinders? Well, that's too much volume, right? So you have to take something out of that. Well, what do you take out? Well, I don't know. Go figure it out. That's one approach, but there's more than one approach. You can do it different ways. So I want to see in your bonus an explanation, right? In words if you have to. Don't just show me integrals and be like, there's the answer. Explain what you're doing. All right, so here's where we were. Line integrals. Remember that picture? We had the curtain. The curtain came through here like that. We found the area of that. And what it required was that we had to find a parametric equation for the curve, right? We had to find some way of parameterizing the curve. And then we had to account for that ds in the integral, right? That ds right there in the integral became this right here. And what was that? What is this? It's the arc length, right? I was talking to, anyone know Thomas Presley? The engineering, teaches engineering here. Anyone know? No? Tom? He's a chair of the math department, but he's actually an engineering teacher for engineering. Okay. I was talking to him about some of the stuff in integrals that students have trouble with, and he's talking about this ds and students not understanding that ds is an infinitesimal arc length, and that he'll be teaching an engineering class and he'll be like, okay, we have a wire and we want to find its center of mass or something, so we take an infinitesimal arc length. And he says that most students are like, huh? So I want to make sure you understand like that ds comes from something, right? Okay. We did that, and then we worked through this. We did that example, right? And we talked about if you want to integrate and you have a curve that is actually multiple curves put together, you can do each one separately. So I think I did that also, right? We did this problem. I think that's where I finished. Yes. So my original plan was to pick up right there. But after this conversation that I had with the engineering department, I want to show you just a little quick extension of what we did last time. So, whoa, hold on, I'm lost now. Day 21, here we go. All right, so let's say that we have a wire in two-dimensional space, all right? 2D, just a wire. Here we go. And let's say that the wire has a varying density. So at every point on this wire, the density is not constant. So maybe the wire was created by taking some piece of metal and stretching it out till it broke or something. So throughout the wire, it's less dense in some places. Make sense? Or maybe it's manufactured that way. Who knows? So we have this now. If we look at that three-dimensionally, y'all kind of see that that's the wire laying on the ground. At every point on the wire, I could take a measurement of its density, and let's say it comes out to be 1. Then here, I plot up 1. If I go out here, maybe it's not 1, it's 0.75, so I don't go up quite as high. And then maybe in the middle here, it's only 0.2 or something. So you can look at that density as almost like measurements sitting above the wire the whole time. And if you find the area of that, that corresponds to the mass of the wire, because you're taking the sum of all the density masses. Make sense? We did this before. We were trying to find the lamina density, right? It was a double integral. Same, the mass, did I say mass? Of a lamina. We did the sum of all the little infinitesimal areas. Here you're just going to sum up all the mass points. So what you get is that the mass will be equal to the line integral over the curve C of the density function, rho of xy. Remember, we've always used rho of xy for density function, ds. And then, without going into detail on it, the center of mass is x bar y bar will be equal to 1 over mass, same line integral, x rho xy ds. And then the y bar will be 1 over mass, y rho xy ds. So in maybe some engineering class, you say, okay, here we have a wire. It has a linear density function is this. let's find the mass and center of mass of the wire. Right? Okay. Well, here we go. Here's an example. I figured we'd work through it. And I don't know how much of this we'll do by hand or how much we're going to let Mathematica do for us. I thought it would be cool to show you how quickly you could do a problem like this if you have a computer. All right? So let's do this. Let's first set this up. We have a wire that's in the shape of a half circle, and its density function is 1 plus y squared. So its density, the density of the wire, is a function of its y coordinate. So first, let me draw the wire. I should have said half unit circle. Unit circle. I literally made this problem up like 10 minutes before I came into class, so excuse me for the adjustment there. That's a circle. That's really bad. That's real bad. There's my wire, okay? So the density at every point is, do you see what I'm saying? It's a function of y. So what is the density at that point right there? What's the density of the wire there? Well, the y coordinate is 1, right? So I plug 1 in here, 1 squared plus 1, so 2. And then whatever we're measuring this stuff in, we don't worry about that right now, but it would be 2. The density would be 2. Now, what if I'm right here? Density is 1. Over here? 1 again. Okay, let's pick something more interesting. How about here? Well, that's supposed to be like 45 degrees, halfway there. What's the y coordinate there? Root 2 over 2. Square it. 1/2 plus 1. 3/2. So we had 2 here, 3/2 here, we had 1. So what's happening is that as we move across the wire this way, it gets more dense, and then it gets less dense. So we're not saying thicker at the top, but you could almost see it that way. It's like got more metal up there than it does down towards the edges. With me? Okay, let's find the mass. Well, the first thing we have to do is we have to find the parametric equation of the curve itself. Well, the curve is a half circle, right? So the parametric equation would be x is cosine t, y is sine t. T varies between 0 and pi, so that'll draw us the top half circle. Then, remember, we need ds, and ds had the derivatives inside of it. So we need the derivative of x with respect to t, derivative of y with respect to t. And then if we take those, put them in there, square them, square root, we just get 1, right? Which just turns out to be dt. So good, ds is dt. And now I need to actually find the mass. The mass will be equal to the line integral over the curve C of the density function ds, which is the integral from 0 to pi of the density function, which was 1 plus y squared. But y is what? Sine t, right? Because we've found a parameter for y. So 1 plus sine squared t dt. Yes? And then we just integrate that. So we could integrate that, couldn't we? I don't think that would be too much work. You could do power reducing formula on sine squared, couldn't you? This is where I was saying I think what I'd like to do is just demonstrate the ease in which we can do. I was going to do this with Wolfram alpha, but maybe not. So we're going 0 to pi. We're doing 1 plus sine t squared dt. That it? Oh, I need to close that off. 3 pi over 2. Everyone okay with that? So 3 pi over 2. Now let's go back to this. 3 pi over 2. Now let's find x bar. X bar would be equal to 1 over the mass, which would be 2 over 3 pi, right, the reciprocal. Integral of same thing, 0 to pi. But instead of being just the rho, it's x rho xy. X is cosine t, then our 1 plus sine t. Oh, that would actually probably be easier to integrate than the previous one, because you don't even need power reducing formula on that one. Okay? I'm just going to copy this, paste it here, and just throw a cosine t in front of it. Zero. And then what's in front of that? 2 over 3, 0. Does it make sense that the x-coordinate of your center of mass is 0? Because this is a symmetrical wire. So the x-coordinate should be 0. The question is, where's the center of mass up and down? So x is 0. Got that? How do we find the y bar? This is 0. Y bar is equal to 2 over 3 pi, integral 0 to pi, sine this time, right? Sine t, 1 plus sine squared t dt. So I'm just going to go in here and replace this with sine. 10/3. So this is going to be 2 over 3 pi times 10/3, which is 20 over 9 pi. Is that okay? Let's get that as a decimal. So I'm going to take that answer times, what was it, 2 divided by 3 times pi. I'm taking the answer and multiplying it times 2 over 3 pi. Wait. Damn it. Okay. That times 1.0. For those of you who have the TI-89, you know the difference between hitting enter and then hitting green button enter. The Wolfram alpha is the same thing. It's giving me the exact answer. So 0.707. Hey, that looks like root 2 over 2, almost. 0.707. So back to my picture here, approximately 0.707. And so, I don't know, somewhere around there is your center of mass. So you have a center of mass that doesn't actually live on the actual wire, right? So it's like a boomerang. Boomerang center of mass is not on the boomerang itself. All right. Make sense? It's just an extension of what we've done before. But I thought it would be cool to just at least show you that. All right. Let's move on. Okay, so now we are going to move on to two other types of line integrals. We have what's called the line integral along a curve C with respect to x and a line integral along C with respect to y. All this is, okay, can anyone tell what's happening here? I mean, like, this is just pretty much the same exact formula we just had with one exception. We have dx instead of ds, right? And dx is defined to be x prime t dt. So let's just talk about that for a second, because I think it's subtle, but it's interesting. We had defined ds to be the square root of dx dt squared plus dy dt squared dt. And I just said that dx turns out to be dx dt dt. Or, right, x prime of t, isn't x prime of t dx dt? So x prime of t, that's the derivative of x with respect to t. The dt How do I write? Remember when we write dy dx, let's say equals x. Then you could write dy equals x dx. We're just moving that dx to the other side. That's what the x prime means. X prime, x prime. I'm trying to see if anyone can tell me what this new line integral is doing. Like there's something subtle. It's the same as this, but something subtle is happening here. Can anybody tell me when you do a line integral with respect to x, can anyone tell me something about y? You're assuming it's a constant. Why? Because the derivative of y with respect to t then would be what? 0. And then this formula becomes square root of dx dt squared, which just becomes dx dt, doesn't it? Sorry. I wrote that down wrong. X prime t. So what now? This is going to be a 0. So when we go and we say, hey, look, we're going to do a line integral with respect to x, what we're saying is that we're going to imagine that y is constant. Y is a constant function. And that whenever that happens, then you're treating your line integral over c becomes this. Now we could do the same thing. We could treat x as a constant, and then we get the line integral with respect to y. And it becomes this formula. Now, a lot of times, as you'll see later, it's not going to happen yet. These two line integrals, one with respect to x and one with respect to y, appear together in the same integral. So we have something like this. Well, actually, I should have wrote this the other way around. If you have the line integral over c of p of xy, so that's just some function of xy dx, so that's the line integral with respect to x, plus the line integral with respect to y of some other function, q of xy, then that just means the sum of the two line integrals separately. Okay? So this is just notation. When you see this, it means this. All right, so here's some of that notation. We're going to do a problem here. Find the line integral over c of sine x dx plus cosine y dy, where c is the top half of the unit circle, x squared plus y squared equals 1, from 1, 0 to negative 1, 0, and the line segment from negative 1, 0 to negative 2, 3. So you have that all in your notes, so I'm going to just go to it now. All right, let's draw our C first. Okay, let's try and draw C. Top half of circle, right?